Hi guys, answers to chapter 6 in the book. So basically, first question wants you to copy and complete the table with the mean. So I didn't put in the data here, but here's your averages unrounded, or your means unrounded, and then obviously I put them into 2 sig figs because all the data was to 2 sig figs. Once you've done that, it wants you to plot a graph of D on the x-axis, S on the y-axis against D on the x-axis. So that looks something a bit like this when you've got your S on the y-axis, D on the x-axis. Now you could change this to Newton meters at this stage. You don't have to though, it's not that important. So I just left it in millimeters. I don't know if you can see this on the screen. That's 100, that's 200, etc. going up. Anyway, plot your line, straight line. It's a nice beautiful straight line. The points all pretty much lie bang on it, so it's really easy to plot. Once you've done that, it says by taking moments about x, show that s equals wd over big D plus a 0.5 w0. Now this is what we do for this. So first of all, we say the clockwise moments is equal to the anti-clockwise moments. Easy peasy. Now there's 2 clockwise moments on this situation. In the book here, which you can see, we have the weight of the load W, okay, times by little d there. So that's W times by little d, the weight of the load. Now, the beam itself is big D long, and the weight of the beam, yeah, must be W0. Okay, where W0 is the weight of the beam. So W0, the weight of the beam, acts halfway along big D. So that gives us big D upon 2 times by W0, the weight of the beam. So these two are the clockwise moments. And then the anti-clockwise moment is simply the force S of the reaction force acting at the full distance D. So that is D times S, or S times D, whichever way you want to put it. So once we've got this, we simply, this is the hardest bit, I suppose, is spotting this. Once you've got this, you just rearrange it and you say WD upon D equals, and then we divide through by D basically, so you get rid of the D. So that becomes S, this becomes, instead of 0.5, you say D upon 2 or 0.5 WD, whatever you want to write, it's the same thing. We get rid of the D basically there. And then this gets divided by D. Now you're thinking, where's this all going to? But I'm just basically getting to what it wants here. Once we do that, rearrange this, make S the subject, W over D times by D, big D plus a 0.5 W0. And that's basically all it wants you to do. Then we've got to be a bit clever, because it then asks us to use the graph to determine the weight of the load W. And that requires us spotting that this here is a y equals mx plus c equation. So we plotted S on the y-axis, as you know. We plotted little d on the x-axis, as you know. Let's put that there so you can see. S was the y-axis, little d was the x-axis. There we go. That means W over D, this much bit here, must be the gradient. And of course, this is the thing that some people find hard to spot. You've got to be looking out for these. And of course, 0.5 over 0.5 W0 is the intercept. So straight away, we can read off the intercept and work out what W0 is, the weight of the beam, and we can calculate the gradient and work out from the gradient we can work out the weight of the actual load that was being dangled off it. Okie dokie. So part 2 says use your graph to determine the weight of the load W. That's what it's asking us to do here. So basically we know W over D is the gradient M. So you simply did a big gradient triangle, calculated the gradient. I got my gradient out to 1.86 times 10 to the minus 2. But I have to warn you, it was a bit of a scruffy one. I didn't actually have a ruler, only a book to do it with. So that was 1.86 times 10 to the minus 2 I got for there, for my gradient. And then they tell you in the book that it's 480 is the distance D, it says it there. Okay, so now we simply multiply D through and we get W. Now my W came out, I can't remember what it came to, but let's say it's anywhere between 8.7 and 8.9, and that'll get you, that'll be a correct answer for that. Okie dokie. Next thing it says for C, The distance of measures to an accuracy of plus or minus 1 millimeter, and the Newton meter was to an accuracy of plus or minus 0.1 newtons. So what we want to think is, where is the error the greatest? Now the error is going to be bigger. The biggest error will be on the smallest readings, because obviously the error is a greater percentage of it. So for example, for the D, we get a greater percentage error if we take plus or minus 1 millimeter out of 40 than we do if we get plus or minus 1 millimeter out of 440. So we want to basically consider which one has the biggest error. So for D, it's plus or minus 1 millimeter out of 40 millimeters. That gives us 2.5%. And for this force, the smallest force, average smallest force, remember, was 1.3, or you should have got 1.3 for the average. So it's plus or minus 0.1 divided by 1.3, and that gives us 7.7%. So of course the force is the greatest error. Okay, that's the biggest percentage error. C part 2 says, without using additional apparatus, discuss the further measurements you use to improve the accuracy. Well, the bottom line is we can look at this and see very clearly that there's quite a range between these first and second set of readings. Therefore, we want to take more readings and get a more reliable average. That'll give us more accurate results. Okay, that's one. Question number 2. It says it wants to draw a scale diagram. Okay, what you want to do here: 9.6 newtons, 4.8 newtons, an angle of 40 degrees between them. Okay, and then you can do the parallelogram or whatever you want to do, but basically you then draw the resultant force in there and measure it off. Now I got 13.6. That's pretty much right, but again, like I say, I didn't have a proper ruler. Okay, I've just got a scruffy old thing because I'm at home, so it might not be very good. So somewhere around 13.6 is what you want to find. Once you've done that, it says that's part A, I think, and then once it says that, it says it wants you to measure the angle between the resultant force and the 9.6 Newton force. So there's our resultant there. There's my 9.6. Measure that angle. Again, I got 13. It should be pretty close to that. Okay, B. It says calculate the resultant force when the same two forces act at right angles. You must not use a scale diagram for this part, and that's something you've got to remember in the exams. If they tell you that, do it, or rather, if they tell you not to do it, don't do it. So you've got to use Pythagoras. Okay. And it's basically going to be the square root of 9.6 squared plus 4.8 squared. That comes to 10.7 newtons. Okie dokie. That is question 2.